Let's work a couple of multiple choice type problems, true false sorts of things that really get us when we're talking about satellites. For problem 25, we're just going to figure out which of these statements are true about satellites. Satellites are falling projectiles. Well, if you remember, that was part of Newton's moon, where if we had a cannon, a very tall cannon, say at the top of the Earth, and this is the Earth, so don't laugh at my pictures. All right. If if we shoot the cannon off and it doesn't go very fast, it'll crash to Earth. If we shoot it off really fast, it'll kind of take off pretty straight. But if we shoot it just right, it'll be in this free fall around the Earth. So yes, satellites are just falling projectiles. The next one, all satellites follow circular paths. Well, what do you think? For the most part, this is not true. I know we approximate them with circular paths, but satellites in general follow elliptical paths. And ELLIP, TCAL. So basically, they're not perfect circles. For our class, we're always going to assume they're making perfect circles. So this one's, no, it's not true, but we're going to assume it's true. The orbital velocity required of a satellite is dependent upon the mass of the satellite. A more massive satellite requires greater speed. Well, remember to do these, we take the centripetal force and we set that equal to the gravitational force. So I'm going to use this picture right here. Here is my satellite that's going around, and here is the mass of my planet. Fc is the mass of your orbiting object, so it's the mass of the satellite times v squared divided by the radius. Remember, the radius is how far from the planet you are. And this has to equal big G, mass of the planet, mass of the satellite, divided by r squared. Now let me change colors here. When you solve this, you see the mass of the satellite always cancels. We have 1r always canceling. So we wind up with v squared is g, mass of the planet divided by r. So the orbital speed, if we square root these, depends upon the planet and how far away you are. So this one is false. The orbital velocity of a satellite does not depend upon the mass of the planet about which it orbits. Well, now we just showed that the speed is the square root of g times the mass of the planet divided by the orbital radius. So this one is also false because of that word not right now, right there. It does depend upon the mass of the planet. So this is really kind of interesting. If you're in orbit around a planet, so here's a planet and here you are, you're orbiting. You're smiling because you're orbiting. Okay, you're going around in a circle. You'll have the exact same orbital speed as the satellite or the spaceship you were on. A high altitude satellite will require a greater orbital speed than a low altitude. Let's go back to that formula we just had. V is the square root of g, mass of the planet, divided by the radius. Now, r is how far you are from the center of the planet. So if here's my planet and here you are, okay, clearly the higher the altitude you are, so higher altitude means you're further from the center of the planet. If this number is large, well, 1 over a large number is a small number, so your velocity will actually go down. So high altitude satellites require less speed than low altitude, so this one is false. By definition, a geosynchronous satellite orbits the Earth in a perfect circle, maintaining the same distance above the surface of the Earth. Technically, this one's false because a lot of times we're talking about a geostationary orbit, geostatio. Okay, for the most part, for our purposes, these two are close enough to the same that we'll say yes. So basically what you'd have is here's your planet, and there's your satellite, and it's orbiting with the same period as the planet's rotating. All right, satellites travel faster along their orbital paths when they're closest to Earth. Let me go back to my speed equation that we just came up with. The velocity is the square root of g, the mass of the planet, divided by the radius. So, if they're close to the Earth, that means this is a very small radius, which means you have a very large velocity. So this one is true. If you ever get confused about this and just need to verify for yourself, what if r is 1 meter? If r is 1 meter, then this is 1 over 1 or 1. Where if r is 2 meters, this would be 1/2. So you see, as you increase the denominator, this decreases your actual speed. All right, I know this isn't a direct correlation. This is just showing you that as you increase this denominator, the velocity has to go. As you increase the denominator, the velocity has to go up. All right, the acceleration of a satellite varies inversely with the distance from the center of the Earth. More distant satellites have smaller accelerations. Well, I think so, because let's look at this. F net equals MA. And if this is equal to FG, which is big G, M1, M2 over R squared. All right, we see that the bigger the radius, you're going to wind up with a smaller acceleration. So this one's true. Now, for any given planet, its speed is greatest when it's closest to the sun. Well, that's true because r is less. And since we know that planets actually follow an elliptical orbit, it turns out they're going fastest here and slowest when they're furthest away. The velocity vector is tangent to the elliptical path. Now, again, we're using mostly circular paths in our class, but you remember, here's my diagram. The velocity vector is always tangent, while the acceleration vector is to the center. And you know what? That is a really horrible circle. Let's do this. Let's cheat a little bit. Let's put in my circle here. We'll play. All right, so if this is my diagram, my velocity vector is always going to be tangent like that. Tangent means it's touching at one point, while my acceleration vector and my net force vector are always to the center. The net force vector is at all times perpendicular to the velocity vector, of course, because the net force vector is to the center. Let me do this. Okay, the net force vector is to the center, because that's centripetal force. And the velocity vector is always tangent, and so those are always perpendicular. To keep the planet from escaping the sun's gravitational field, the net force vector is greatest when the planet is furthest from the sun. Well, no, that's not the case at all. As a matter of fact, the net force vector is actually largest when it's closest to the sun. So this one is false. All right. Oh, goodness. We've already covered these. That's great. Make sure when you're doing multiple choice problems for any test or true false, you read carefully. Just read it carefully. Watch for words like always and never. Okay, those are warnings that something might not be true. If you can come up with a counterexample, then this right here will be an indication that your answer is false.